Okay, hello and welcome to my channel. Today we're going to talk about the central potential. So first, let's look back and appreciate the way we've gone through, since this is when the Schrodinger equation is going to change again. So let's remember our first Hamiltonian that we dealt with, the 1D time-independent Schrodinger equation of psi is equal to E, or maybe just plus V of x. And then we look to the 3D, the 3D Schrodinger equation. And now it's gonna be something that is, well, kind of similar to this, but not really. It would have the same notation as the Laplacian here, though. So the Schrodinger equation in central potential is, or in the spherical space, it would be something like this. Would be minus h bar squared over 2m, the Laplacian psi plus v of r, psi equal to e psi. And psi is a function of r as well. Again, since this is the central potential, we bring any x to the radial, which is the r vector. Okay, so a little bit about central potential. This is something that is spherically symmetric, and it is invariant under rotation. So the way you imagine it is kind of weird. In 2D, it would look something like this. A sinkhole. You would like to imagine a sinkhole, basically. And in 3D, it is a sphere that is hollow inside, and outside there are things that is like pressing it down. So kind of like an infinite square wave potential, but you turn it into a sphere and look at it in 3D. Right, so yeah, I will leave them here for now. Okay, and let's address our Laplacian here in the spherical space. Our Laplacian is equal to 1 over r squared d theta. Okay, I don't know if I'm gonna be able to write this correctly, but it is something. I will try. 1 over sine d theta plus 1 over sine squared. Remember this part. D theta. Okay, so I believe this is your Laplacian. Okay, so this, you can also write this as the radial part plus the angular part. I'll write it as A. So basically the domain of this is r, theta, and phi. So yeah. And when talking about the spherical, central potential, you're gonna have, well, two facts that you might want to note down. The first one is that, well, you have this function, this equation. So the first one is minus h bar square times the angular part of the Laplacian would equal to L square. So L square here is the total angular momentum. We're going to talk about that in the next video, the angular momentum. So now you just have to know this first one. The total angular momentum is the sum of its three components, which are Lx, Ly, and Lz. And you square all of them. Okay, and from here you can get the second thing that you have to remember is that this equation here, it is relevant and it is very much usable in the case where you have to consider two bodies, meaning something like a hydrogen atom, which you can see like right here, this the hydrogen atom. Anyways, so in a two-body problem like the hydrogen atom, you would have, well, the potential of x1 and x2 would be equal to the potential of the absolute distance between these two guys. Okay, so that is the hydrogen atom. So these are the two things that you have to remember for now. Later on, you're gonna kind of do these and understand these instead of remembering these. Okay, so that would be it for central potential. Goodbye.